So we're now on page 3 of the lab. We just finished calculating a confidence interval for a proportion, which was a review of last week. Now we're going to move on to conducting a hypothesis test for a proportion, and we'll finish with dealing with means. So on page 3 here, we see on the top of the page a short passage giving us some information. We see that we have a null proportion value of 0.231. We're told to conduct a two-sided hypothesis test with the alpha level of 0.05. So this is similar to a passage you may see on an exam. There's important information in this passage which you'll need to conduct your hypothesis test. One is the null hypothesis value. 2 is whether or not it's a one-sided or two-sided test, and 3 is your alpha level. So once we have that information, we can conduct our hypothesis test using our point estimate from our sample, which, if you recall, was 14.3%. That was our, from our sample, we found that 14.3% of mothers smoked while they were pregnant. That's our point estimate of the true population parameter. And what we would like to know now, basically, is how unlikely would it be to obtain a sample with a proportion of 14.3%. A sample of 800. How unlikely would it be to obtain a sample of 800 mothers, a random sample, with a proportion of 14.3% if the true population value was 23.1%. So we have our population, our hypothesized true parameter, which is 0.231. So if you imagined the population of pregnant mothers with a proportion of 0.231, or 23.1% of those mothers smoked while pregnant. So that's our population. And remember, last week we learned how do we create a sampling distribution from that population. Remember that the mean of our sampling distribution is the true population parameter. So we are, in this case, assuming that the population of pregnant mothers, the proportion of those mothers who smoked is 0.231 or 23.1%. So what we would like to know is how unlikely would it be to obtain a sample of 800 mothers from that population. How unlikely would it be to obtain a sample where 14.3% of mothers smoked? So in a sampling distribution, which we are assuming is normal, and why do we assume the sampling distribution is normal? So we use our rule of thumb, which we've learned. If you go to page 5 under hand calculations, you'll see we first need to assume a normal sampling distribution. Again, we can conduct an exact binomial test, but for now we're going to deal with the assumption of normal sampling distribution. Now we see here that our assumption of a normal sampling distribution has been met. NP and n times 1 minus p are both greater than 15. Note that in this case, unlike the confidence interval, we're using our null p, because we're assuming that the true p is 0.231, right? So we're using our null p, and we want to know about the sampling distribution from a population with a value of 0.231. So that's the p we would use, not the sample p. So now in a sampling distribution from a population with a p of 0.231, how unlikely would it be to get a sample with a p of 0.231? 0.143. So we'll end up with a z-score. Now, these the concepts we learned about normal distribution and z-scores are going to pop up again now, and if you understand those concepts, you most likely won't have any problem understanding hypothesis testing. It's the same idea. We have a normal distribution. We're assuming our sampling distribution is normal. Now when we get a z-score, our z-score is telling us how many standard errors from the center of our distribution, or the mean, does our value lie. We learned how to do that with a data distribution, with a normal data distribution. The only difference in this case is we're dealing with a sampling distribution. So we have a distribution of sample values, and we want to know how far off our sample value would be, how unlikely would it be to obtain a sample value of 0.143. Now again, because this is a two-sided test, we're going to get a z-score, and we would like to know in either direction. So if you picture a normal distribution, we're not asking, whether a one-sided test would just be a one-tailed p-value. For example, if we hypothesized that the true population parameter was less than 0.231, we would assume a z-score of less than 0. So we would assume a negative z-score. And if that z-score is so unlikely, and by so unlikely, that depends on our alpha level. So if our alpha is 0.05, we would need to get a z-score which has a cumulative probability of less than 0.05 in order to reject our null. So in this case, we know that we're going to end up with a negative z-score, but we're still conducting a two-sided test, so we'll end up getting a p-value for the absolute value of the z-score. So for instance, if our z-score was 2, we would get our p-value for a z-score of 2 or more extreme in either direction on either side. So -2 and 2, to the right of 2 or to the left of -2 in a normal sampling distribution would be our p-value. If it was one-sided and our hypothesis was stated in such a way that we hypothesized that the true population parameter was less than 0.231, we would just be obtaining the left tail for our z-score, which in this case we know our z-score is going to be negative because our sample value is 0.143, and we're assuming a true parameter value of 0.231. Now remember, the true population parameter value in a sampling distribution, a normal sampling distribution, lies in the center, and the z-score for that value is 0. So any value less than 0.231 will give us a negative z-score. Any value greater than 0.231 will end up giving us a positive z-score. Once we get our z-score, we're going to get a p-value for that z-score. And if that p-value is less than 0.05, we'll reject our null. If it's greater than 0.05, we'll fail to reject our null. If it's a one-sided test, you'll use, depending on the direction of your test. We'll get into one-sided tests more later on, but once you understand the concept here, and also how to deal with the normal distribution and calculating probabilities, you shouldn't have any problem going from a two-sided to a one-sided test. So what we see here on page 7 is a brief description of calculating a one-sided test and how it would be different compared to a two-sided test. But again, later on, we'll get into more description of this, and also in lecture we'll talk about this more. And but for the most part, we'll be dealing with two-sided tests. So let's learn how to conduct this test in SPSS. Again, using our Analyze menu. We first see here that we stated our null and alternative, which is what you'll need to know how to do. This is our null. Our null hypothesis is that the P, which is the true population parameter, is in fact 0.231 for pregnant moms. This, we're assuming smoking prevalence for pregnant moms is 0.231. And our alternative hypothesis is saying that smoking prevalence for pregnant moms in North Carolina is not 0.231. So we'll test that now, and we'll use our Analyze menu again. We'll go to Non-Parametric Tests, One Sample. Now in our pop-up window we have three options here. What is your objective? We're going to click on Customize Analysis. In the next tab under Fields, we need to move all of these variables over. And the only variable that we move over to test field is the one for which we're conducting the hypothesis test, which is, in this case, smoked during pregnancy. So an easy way to get all of these variables to this area here, you click on your first variable, it should be highlighted. Now you're going to hold down your Shift key and click on the last variable there, and all your variables will be highlighted. You're going to move those over. So now the variable we're interested in right now is smoking during pregnancy. So we're going to move that over to test field. That's what our hypothesis test will be based on, is smoking prevalence. So then that looks good so far. Now under settings, you're going to choose Customize Tests. You're going to check Compare Observed Binary Probability to Hypothesized. You're going to click on Options. Now hypothesized proportion is our null value, which we remember is 0.231. So here we're going to enter that value, 0.231. Now you need to specify success value. In this case, we are interested in the smoking prevalence, in other words, the proportion who smoked. Now if you remember in variable view where we code our variables, smoking was categorized as a 1, and not smoking was categorized as a 0. So this value we need to tell SPSS, since we are interested in the proportion who did smoke. We're not interested in the proportion who didn't smoke. We're interested in the category of 1. So success value here we would enter as a 1. And now in this window here, we're done. We have our null hypothesis value. We specify our success value. You can click OK now. Now under test options is where you would choose your alpha level, which you can change to 0.01, you can change to 0.1, or any value you like. In this case our alpha is 0.05, so we'll leave that as default. Everything else is fine. Now to get our results we click Run, and you'll get your results pop up here, which is the same output you see in the file, in the lab file. And the results are not too informative. It just lets us know whether or not to reject our null, and it gives us a p-value. But remember that this p-value is a one-tailed p-value. Now what we want is a z-score. Now knowing this one-tailed p-value, we could obviously know that the two-tailed is going to be less than 0.05. If the one-tailed is 0.000, two-tailed is going to be less than 0.05. If, for example, you saw a p-value of 0.03 here, let's say that the p under sig is at 0.03, and you rejected your null based on that, you would be wrong in this case because this is a two-sided test. So we're not looking for a one-sided p-value, we're looking for two-sided. So if this one-sided p-value, if this p-value here is 0.03, that would mean that the two-sided p-value is 0.06, and in that case you fail to reject. So remember that this is a one-sided, this p-value is one-sided. So we'll see how to get a two-sided p-value. We'll see how to get exact p-value in Excel next and in SPSS. But the first thing we want actually is, besides the decision and the p-value, is a z-score. We want our test statistic. In order to get a test statistic, we have to double-click on this output here. If you see a little pop-up came up, double-click to activate. We can double-click this window here and we'll get another output. In this output, you can see under standardized test statistic a value of negative 5.866. That is our z-score. That's our test statistic. So what is that telling us? That's telling us that in a sampling distribution with a mean value of 0.231, which remember our null value is 0.231, so it's saying that in a sampling distribution, in a normal distribution where the center is 0.231, which again remember that value 0.231, if you were to calculate the z-score, would be 0, the center of the normal distribution. So in a standard normal distribution based on the sampling distribution with a mean of 0.231, this z-score is telling us that our sample, or a value of 0.143, remember our value from our sample for smoking was 0.143, or 14.3% of our moms from our sample of 800 smoked. So what this is saying is, if you were to look at a sampling distribution, in the center is 0.231, 0.143 obviously is below that. This is saying that that value of 0.143 is 5.866 standard errors below the mean. It's to the left, it's 5.866 standard errors. So what we want to now find out is a p-value for our test statistic. Now remember that in a two-sided value, we are interested in the probability of z-score of 0.5866 or more extreme in either direction. So if you picture the sampling distribution, we have negative 5.866 on one side, we have positive 5.866 on the other side. So the p in the tail above 5.866 and the probability in the tail below negative 5.866 is what we are going to obtain. That's what we do when we conduct a two-sided test. We're not interested in the sign, we're interested in the absolute value, and we want to know what's the probability of finding a value as extreme or more than that in a two-sided test. If it was a one-sided, we would only simply be interested in the p in one tail, depending on the direction of our hypothesis, whether we thought it was more or less. We would either be interested in the left tail or the right tail. So in this case, it's a two-sided test. So we have our z-score of negative, we can close this window here. We have our z-score, we can write that down, 0.5866. So now we know our z-score. What we would like is to get a p-value for that z-score. So if I were to open an Excel file, a blank Excel file, now remember we learned how to calculate, if you recall, on a previous lab, probability distributions in Excel and SPSS. We learned how to do those calculations in Excel and SPSS, working with a normal distribution. So in this case, if we wanted to get this p-value for our z-score, we could use the normdist function, which we learned how to do. Now remember, this is a z-score of negative 5.866. Now the mean for a standard normal distribution, remember, is 0. And the standard deviation for a normal distribution is 1. Now we want the cumulative probability, which is the probability of a value of 5.866 or less. So we have true, and we click enter. Now remember, this is the cumulative probability, so we are being given the left tail, which is, at or below our value. Remember, we conduct a two-sided test. We want the two-tailed probability. So since it's a symmetrical distribution, we can simply multiply this value by 2. And that's our p-value for our z-score of 5.866. That is the p-value. That's the two-tailed p-value. This is the one-tailed p-value. So we have our z-score, we have our p-value. Now we compare our p to our alpha, which we chose as 0.05. This is much less than that. That makes sense because a z-score of 5.866 is way off in the tail. Remember the rules we learned, that 95% of a normal distribution falls within 2 standard deviations, in this case standard errors, because we're dealing with a sampling distribution. So in a normal sampling distribution, about 95% should fall within 95% of our sample values should fall within 2 standard errors, and almost all should fall within 3 standard errors. So 5.866 is very far off from the center. It's almost 6 standard errors away from the center. So that the probability of getting something that extreme, as you can see here, is very, very low. And that's obviously less than our alpha. So we are rejecting our null in this case. We reject the null and we say that the true population parameter is not 0.231. In fact, our findings indicate that it's less than 0.231. We could, again, now the next step in this would be to get, some values, what we thought the population parameter was, and we previously did that when we calculated a confidence interval. So doing hypothesis tests and confidence intervals should go together. You should not just stop and say that, okay, it's not 0.231. You should also follow it up with a confidence interval to give some values. You're saying it's not 0.231, but also you're going to give some values which you are saying we assume that the values are between 0.12 and 0.17. We're 95% confident of that. So now we know how to conduct our hypothesis test, and we know how to do our confidence interval. And this is what you should be able to do on your own in SPSS. And in the case of the hand calculations, that's following, beginning on page 5. Now again, we are assuming a normal sampling distribution. This is the formula to get your z-score. We see here that the z-score we obtain with the hand calculation is consistent with what we found from SPSS. So now, what are your conclusions? Is your p-value greater or less than alpha 0.05? So remember, we're getting the probability of the absolute value of a z-score of 5.866 or 5.87 rounded off because it's a two-tailed test. And we found out that our p-value, our exact p-value, was 4.46 times 10 to the negative 9th, so it's well below our value here. Now, so that concludes the hypothesis test for proportion, and next we are going to move on to dealing with means. So here on page 7 is some extra information about this, and so next we'll talk about means.